0 in this funky form, right? But now I need to know what the commutator of x and p is. Okay, so let's investigate the commutation relation, the commutator of x and p.
Alright, so just to stop for a sec, a minus and a plus are just operators that would be something.
Yeah. We're defining them that way.
We're defining them now, so we're going to plug that in after. And
look at this as a big trick. Alright, so everything I have done is legitimate, and at the end is going to be a big kicker to the trick.
Okay, but just the form of x comma p, I don't really know what to do with x comma p.
That's why I'm doing it now.
Mathematically.
So let's figure out what the commutation relation of x and p is. But look at this as a trick, and at the end you're going to get the punchline. And when you get the punchline, you're going to say, oh, now I know why you did that trick.
What does it mean to have x comma p? What does that even mean in that equation?
It's this. It's the commutation relation. Let's investigate it. So,
all right.
Let's investigate x comma p. The commutation relation of x comma p equals what? All right.
It's defined right there.
What's that?
It's defined. The commutation relation is defined right over there. It's saying that if
it's obviously not 0.
x times p minus p times x.
Right, but we want to know what the answer is.
It's obviously not.
But either equals 0 or it doesn't.
They're commutative or not.
We're going to see.
If they are commutative, then we're going to use this trick. If they're not commutative, we're going to do something else.
No, we'll say, let's fall through it. So here's the scoop. The trick works. So trust me, follow through the trick. And then when you get all done, you'll go, boy, those guys are clever. Alright? So this is just a trick. Alright? Now, well, here's what Griffith says, is that operators and the commutators are notoriously a pain in the butt. Alright? So he said to figure out what operators are, throw in a test function, and then at the very end, throw away the test function and see what's left. Alright? So, according to Griffith, this is what you want to do. You want to do x comma p on some test function of x. Alright? So this is called the test function, and then in the end we're going to toss it away to get the answer up here. Everybody okay? Okay, so let's do it. By definition, this is x p minus p x of f of x. Okay. The operator for position is x, right? And the operator for momentum is minus I h partial. Okay, so this comes out to be x p times f of x minus p x times f of x. Now let's put in what these operators are. This is going to be x times minus I h partial with respect to x of f of x. Everybody with me?
Mm-hmm.
Minus I h bar partial with respect to x. Okay, that's p. And then it's going to be x times f of x. So this equals minus I h bar times x and the partial of f with respect to x. Okay, now let me see. So minus, and then I'll take out the minus I h bar. Okay, and then it's going to be the partial with respect to x of x times f of x. So this equals minus I h bar times x partial of f with respect to x minus the partial with respect to x of x f of x. And this equals minus I h bar, big brackets, x. Oh, instead of saying partials, because we're just one dimension, I'm going to say df dx, we're going to use a total derivative. Then minus what? What's the answer over here? How do you do that? Partial with respect to x of x times f of x. By what? The product rule. So what's the answer?
So x plus partial x.
Okay, so tell me what the answer is.
F of x minus x df dx.
Okay, so let's differentiate the first
So it's
one.
that.
It's going to be the derivative of x
Yeah,
over
derivative
x.
of x now.
X. So it's going to be f of x, right? Minus, and now let's do the other one. It's going to be, take this one times the derivative of that one, so it's going to be x times df dx. What happens to this? Goes away. This equals plus I h f of x. All right, so in other words, I have the commutator of x and p f of x equals I h f of x. And then what's the trick? Get rid of the f of x. And what am I left with? The commutator of x and p equals, no longer question mark, equals I h bar.
And could we do that the other way, just with x and p, just plug them in and subtract that out and get the same answer, or no?
As long as you're mathematically consistent.
Positive IH.
Okay, so let's watch this. Okay, so now we go back here. Now we rewrite h0 equals h bar omega, a minus dagger, a plus dagger, minus, minus 1 over 2 h bar. And then on the top it's going to be I
H bar.
h bar. H bar minus, hold on, wait a minute, I'm not sure I have a minus in there. Did I miss a minus somewhere?
There's a mistake in the top one.
All right.
I think I need the I right here. I think I missed an I right here.
Wait a minute. The original thing we were doing in all
I need
this.
an I right here. Hold on a second, please. There's going to be an I right here. Right?
Oh.
So then I need an I
There's the I
here.
of omega.
Right? And then it's going to be I squared. That's going to be plus. Yeah. So that cancels that. Yeah. So this works.
Plus 1/2.
Yep. So it's h bar omega. Well, I'll write it up. It's going to be, well, h bar omega, a minus dagger, a plus dagger, all right, plus h bar omega over 2.
So it was an I.
Wait, so the one you changed was
Or is it a minus?
instead of 1 over, you made the I over 2H, right? H bar.
Where'd you get that second I?
You have to H bar omega over 2. Yeah.
Where'd you get the second I? It's like
I don't know,
I
so
times
make sure I get it right. So go through and do it.
Where did the second I come from? I'm just wondering.
So find it. Right? That's your job to go home. Make sure I've got it all right.
Yeah, because you had the I and omega, and then you took out.
So I think I missed it right over here. Is that right?
Yes, that's what you missed, because you had the I and omega, and then.
Where's my mistake? I mean,
The top?
At the very top line, when you came from here to here, you threw a minus sign in there. You flipped them around. You were very careful on the left to keep the PX, XP, PX over here, and then you switched them for some reason. I'm not sure why.
well, I have
Because it should be
minus. Oh,
And then you dropped a minus sign in front of them.
so I double dropped a minus.
Yeah.
Yeah, there's a famous story in graduate school that there was a professor that paid a graduate student to just keep track of the minuses and the double minuses. Yeah. So
All right. So question.
yes,
You said that all this just came out to I H bar.
yes.
We originally started because we had this complex differential equation that we had to solve.
Yes.
Are you telling me that that would have come out to I H bar?
No. What did I tell you comes out to IH bar?
The operator X, the combination between
The commutator.
commutator XP.
And is that the whole thing?
Oh, that's not the whole thing.
That commutator is just this little chunk of it.
Which is what you plugged right back
Yeah.
in just now.
All right, so
That's where the I comes from.
okay, so here's the scoop, guys, is that you end up with H0 equals h bar omega, a minus, a plus, and I have minus h bar omega over 2 in my notes. So what we should do for homework is let's make sure we get it, all right? So go through and get it, and you can follow through on purpose.
I see why, because when you drop down from.
Yeah, so this is correct. So guys, go through and follow all the pluses and minuses and get that right. All right? And so here's the scoop. When you've done all that, when you've gone through and done all that, we initially we were trying to solve what? We were trying to solve H0 psi n equals En psi n. All right? And the original differential equation was, I'll write it out in full. It was minus h bar squared over 2m d squared dx squared psi n plus 1/2 m omega squared x squared times psi n equals En psi n. That was the original differential equation?
Yeah.
Okay. We now have a new representation of this problem, all right? And this new representation is going to be written as h bar omega times a dagger minus a dagger plus minus h bar omega, minus 1/2 times psi n equals En psi n. So, what's the only thing we've done, guys, this whole time? Okay, we've just we've done a new representation of the Hamiltonian. Okay, we wrote it. It's a new representation. Right? But and all we've done is algebra, guys, but we've used operator algebra. Right? We've introduced a commutator. Everybody okay? Okay, so the claim is this is going to be easy to solve. So this is going to turn out to be easy.
Easier than the brute force.
And easier than the brute force. And these are called raising and lowering operators. And you can use it in other places and stuff. Whenever you have a harmonic oscillator potential or a differential equation like this, you can do this. Yep.
If I want to solve the harmonic oscillator and then put the solution here.
That works for, you mean if you want to go brute force and solve a differential equation?
Yeah.
It works beautifully. Okay, the answers are going to be these things called Hermite polynomials. Okay, remember when we solved for the 1D well, we got nice sines and cosines. They don't have a name, they're just sines and cosines. When we solve for the harmonic oscillator, we're going to get the answer of these functions that are called Hermite polynomials. And if you go through and you do a brute force way, which Griffith does in full glory, all right, you get Hermite polynomials. But this, trust me, so we went through a little bit of a pain here. The next step to solving this is going to be a breeze. And we're going to be able to do it all over the place. Whereas doing it the brute force way is going to be hard. But make no two mistakes about it. Both ways are equivalent, and both ways come up to the same answer.
I'm going to trust you on this one.
Yeah, you got it. And you don't have to, but this is the way to go. Take a look at the book. So look at Griffiths and see how he solves it. So it starts on let's see.
So that's what I didn't know what those raising and lowering operators were.
Yeah, so Jeremy, I'm going to cut you off on page 51. Griffiths does the analytic method.
The harmonic oscillator starts on page 40, goes to
This was